Good morning, good afternoon, and good evening. Welcome back. This is class number 16, believe it or not. All right, so as promised, here is the third problem set. There are 9 questions, but only 4 of them of your choice are due. First 3 questions are closely related and maybe familiar to some of the system algebraists, but this is one of the important methods, tools, tricks, call it what you will, that are being used in connection with ultra powers. And other questions are basically a grab bag of results related to what we were doing recently. And talking about grab bags, basically, what we are doing right now does look like a grab bag, but trust me, everything is going in one direction. So our next goal is to prove that OCA implies all automorphisms of the Kalkin algebra are inner. It just turns out that in order to prove that, one needs to prove all sorts of things from different subjects. And anyway, so without further ado, let's move on to today's bit of this grab bag. All right, so last class, as you know, was sort of a little break from that. We just went over the homeworks. So this was defined exactly 1 week ago. Here is a reminder. Here we have a star homomorphism phi. Here is phi, which is a star homomorphism between 2 coronas, Q of A and Q of B. And lifting of phi is phi star. Here star is in subscript, so this is not the adjoint, definitely. Is a map from multiplier algebra of A to multiplier algebra of B, which has the property that the diagram commutes, right? So these are quotient maps. Here's phi, here's phi star. Now, if the axiom of choice implies that phi star exists, you just need to choose a representative from each equivalence class. But the point is that we'll have to work hard to actually construct, to prove that there is a phi star which is nice. Eventually, it's going to be just a conjugation by partial isometry. But getting there, we'll have to do this in a few stages. And anyway, so I just see here there is a typo, not that phi is a lifting, but that phi has a lifting on P of X. All right. Okay, so our next task is to prove that this phi star has at least some reasonable properties. And those properties will be used later on to put a hold, to get a hold on the structure of phi star. So, okay, so that's what the following lemma is about. This is not exactly lemma 1732, but it is close enough, pretty much the same lemma in some sense. Here, A and B are just non-unital system algebras. And statement is that every star homomorphism phi between their coronas has a lifting phi star, which has these 3 properties. Phi star of A is self-adjoint if A is self-adjoint. Phi star is a contraction, as operator algebraists would say. Norm of phi star of A is less or equal than norm of A for all A. And finally, in our main case of interest, if M of B is B of H, then we can assume that phi star of P is a projection for every projection. So basically 3 properties that we'll need a phi star to preserve is being self-adjoint, being projection, and norm being less or equal than something. All right, so now this is very standard, but since this is a course, I guess I should go over standard facts. Now, this lemma is really the following lemma. Let me just add a page here so that we can. So here is a more general lemma. If A is, so here, capital A is East algebra, J is an ideal, and remember, as always, ideal means a two-sided, norm-closed, self-adjoint ideal. If A is an element of the quotient, if it's self-adjoint, then it can be lifted to a self-adjoint element A0 of A, so that the image of A0 is equal to A. Now, why this implies this here? Well, let me just say it without writing it. You see, if A is self-adjoint, then the image, actually, maybe I should just say it for 1. So, okay, why 1 implies 1. This looks silly, but I guess you know what I mean. I mean, why this 1 implies this one here. Well, if A is equal to A star, then also phi of A is equal to phi of A star. And all that you need to do is lift this to a self-adjoint. So basically, this is going to be the A from here. If you can lift this, so if A0 is in B of H, such that P of A0 is phi of A, and A0 is equal to A0 star, then let phi star of A be A0, except that here I should have put dot here, because this is really a image in the quotient map. So basically, we are going to construct phi star element by element. So for each element, we are just choosing something in the equivalence class, modulo compacts of its image, and just choosing it so that it has desired properties. Proofs of 2 and 3 are virtually identical. Because I mean, for 2, we are just using the fact that star homomorphism between C star algebras is a contraction. That norm, so let me just say it. One should always, oops, there is no star here. Norm of phi of A is less or equal than norm of A always. So from there, the proof of 2 is very similar. And for 3, that projection leads to projection. Again, this is if the original algebra is B of H. It is an exercise to prove that you cannot always lift a projection to a projection. All right. So we move on to prove the second lemma. For 1, well, just if B is in A and P of B is equal to A, right? So we just lift it somehow. B is maybe not self-adjoint. Well, just let A0 be 1/2 B plus B star. And then A0 is self-adjoint. And what is P of A0? Well, it is 1/2 A plus A star, but A is self-adjoint, so this is just A. Right, so okay, 1 is by far the easiest of the 3 parts of this proof. I'll move to part 3, because part 2 will take a while. So for 2, need more lemmas, and they're coming up. Okay, so 3, what was 3? So we have projection P in Kalkin algebra, projection. We want to lift it to a projection in B of H. Before I go on with the proof, I should say a few things. Instead of B of H, you can have much wider class of algebras, so-called algebras with a real rank 0. If you don't know what it is, never mind. I'm not going to be using it. There is a proof in my book of that case, but what I'm going to do right now is give just proof for B of H, which is much easier than the general proof. In particular, I don't even have to define the general notion, but it's just good to know that this is true in a wider generality, but not for arbitrary Swift algebra. Okay, so now, by 1, you see projection is self-adjoint. So by part 1, I can lift P to a self-adjoint element. So fix sum, actually let's call it A0. Fix A0 in B of H, such that A0 is equal to A0 star. And P of A0 is equal to P. Now we need to, this A0 doesn't have to be a projection, but what we do know is that because projection means that P squared is equal to P. So what it implies that A0 squared minus A0 is compact. Right? This is because P squared is equal to P. Right? So this goes to compact operators. All right. So what do we have now? We have a compact self-adjoint operator. Right? This is still self-adjoint. And there is spectral theorem for self-adjoint compact operators. So by the spectral theorem for compact self-adjoint operators, sorry, just a second. I just need to do something. All right. So by the spectral theorem, this, let's call it B. So we can write B in the following form: sum over J Rj times, okay, I shouldn't be using P because we already have P there. Let's call this Qj, where Qj is a projection of finite rank. Rj is a real number. Also, Qj and Qk are orthogonal if J is different from K. And this sum, right, so this is an infinite sum, so I have to justify what am I talking about. So this is convergent in strong operator topology. All right. So now let's see what do we know? Now, since B is, oh yes, another thing also, Rj's are in R, but also Rj's converge to 0, right? Because we know that B is a compact operator. Okay, so now let's look at the few things. So if we take just sum of all Qj's, let's call this Q. Oh yes, by the way, note that all of these projections commute with B and with A0. So then 1 minus Q, actually, let me just write it down. Oops. So Qj, okay. Spectral theorem doesn't talk about A0, but it talks about B, so Qj be a commute for all J. Right, then 1 minus Q A0 is a projection. Why? Well, because Q commutes with A0, and all the, let me see, where is it? Remember, B was A0 squared minus A0. So actually, the easiest way to think about this is just to look at the spectrum of A0 as well. Just put this in brackets. So okay. So what I want to say is that each Qj commutes with A0. I thought it was obvious, but right now, let's see. So B is A0 squared minus A0. So what do we have here? Basically, continuous functional calculus. B belongs to, oh yeah, sure, right, yes. Silly me, sorry. Because everything, if you look at C star of A0, this is abelian, right? Because A0 is self-adjoint, and all of these elements, B and all the Qj's belong to that abelian C star algebra. Yeah, okay. Now,
but sorry, Ilijas,
yes.
why Qj belongs to this abelian C star algebra? Qj is...
Well, it's continuous functional calculus. You see, B belongs there. That's clear, right?
Yes.
And now, how do you get Qj? Well, okay, I didn't say that. Rj's are all distinct.
Mm-hmm.
So how do I get Qj out of A0? Well, just look at the function, which is, okay, spectral theorem. Why does Qj belong to C star algebra generated by B? Well, look at what is, so look at the function f, which sends Rj to 1, and f, which sends everything else to 0. You see, spectrum of B is discrete. Rj is an isolated point of the spectrum of B. Spectrum of B looks like this. So it's these isolated points, R0, R1, Rj, there is 0. And now if you just look at function, which is, this is Rj, which is 1 here and 0 everywhere else. And if you apply, so f of Rk is 0 for every k distinct from j, then f of b will be Qj.
Okay, thanks.
Right, Qj is a spectral projection
Yes.
of B. Okay, thanks for asking. So, okay, so what do we have? Now, now the point is that, okay, 1 minus QA0 is a projection. In all these other places, it may not be a projection, but now if you look at the following function. Okay, used up f. Look at function g, which maps the interval, well, which maps the reals into 0, 1. So g of t is 0 if t is less than 1/2, and g of t is 1 if t is greater or equal than 1/2. Well, this function is not continuous, but you see the spectrum of A0 is disconnected. And what are elements of the spectrum of A0? Well, if you look at, okay, let me say it this way. So the set of all elements of form t minus t squared for t in spectrum of A0 is exactly the set of all Rj's for j in n union 0. Right, because this is the spectrum of B, which is A0 minus A0 squared. Okay, so now below, at each one of these projections Rj, t minus t squared is equal to Rj, but it can be either greater than 1/2 or smaller than 1/2. And now g of A0 times Qj is, here. So this is a projection for every j. Right, you see, I have no problem applying g here because this is operator of finite rank. So its spectrum is disconnected. And now just let P0 be sum of those g of A0 Qj over all j in n plus what we already said was a projection 1 minus q times A0. This is a projection, and just checking that spectrally everything works, we get that P of P0 is equal to our projection P. Right, so just the trick was to essentially do this at each one of these finite rank spaces, and that potentially infinite space on 1 minus q. Okay, any questions? All right, so that leaves us with this second part of the lemma, namely proving that phi, we can choose phi star to be to be contraction, not norm increasing. And that will take some continuous functional calculus. So here it is. Now, this is called corollary for rather silly reasons. So just don't worry about it. It is stated as corollary of what's going to come next. but actually it can be proved without what comes next, and the proof is easier. So I'm just calling it corollary here in order to comply with what is in the book. And here is a statement. So suppose, and remember, we are just proving, let me just remind you so that you know, why am I doing what I'm doing? So proving 2, that without loss of generality, norm of phi star of A is less or equal to the norm of A for all A. So this is, oh yes, actually, while I am at that, before I proceed to this corollary, let me just tell you why is this easier when an operator is self-adjoint, and then we'll move on to general case. So I'm just trying to pull this here. Okay. Okay, so the easy case. So if A is equal to A star, well, we already know that we can choose phi star of A to be self-adjoint. So choose B such that B is equal to B star, and which has the property that phi of A is equal to P of B. I just have to stop for a moment and sort of apologize. You see, I always prefer to use different sorts of symbols for objects from different algebra. Here it is being all jumbled up. A is in the Calkin algebra and B is in B of H. I hope this is not too annoying. I don't see a more reasonable way to handle notation here. So anyway, so we have B such that B is equal to B star, and we want to prove that we can assume that norm of B is at most norm of A. So now, continuous functional calculus. So let F mapping R into R be defined as follows. So F of T is minus norm of A if T is less or equal than minus norm of A. F of T is just T if T is between minus norm of A and norm of A, and it is norm of A if T is greater or equal to norm of A. All right, so this is a piecewise linear function. And by applying F to B, I'm just truncating B where needed. So let phi star of A be okay. Yeah, right. So let phi star of A be F of B. Okay, well then F of B is self-adjoint, right? Because this is a real function. If you apply a real function to normal element, you get a self-adjoint element. Also norm of B. Well, norm of B is equal to the maximal value of the spectrum of B, but spectrum of B is the range of F, and range of F is included in the interval between minus norm of A and norm of A. So it is norm of B is at most norm of A. And just one more thing, actually I don't even need new page for that. Just one more thing we need to check. We need to check that P of F of B is equal to phi of P of A. But now P of f of b, well, you see, look at this. Okay, I'll just write it. So it is the same as f of p of b. This is a self-adjoint element, and f is a continuous function. So continuous functional calculus, remember, it commutes with star homomorphisms of an algebra. So it's the same as f of p of b, but what is p of b? Well, it is f of phi of p of a. And what is phi of p of a? This is phi of p of a because the norm of this is at most norm of a. So applying f to something that has norm less or equal, the norm of a doesn't change anything because you aren't truncating anything. Okay, so for normal elements, okay, I want to say for self-adjoint elements, this is easy. For normal, the same for elements that can be lifted to normal elements, this is the same. But in general, we need a few more tricks. And that's exactly what I want to do next. So here is, sorry, trick number one. We'll need, basically, I'm proving a sort of a circle of lemmas with a common theme. We'll need some of them later on. And I'm just using opportunity to showcase some continuous functional calculus here. So this is this corollary is not directly related to what we are doing right now, but it will be useful later on. And here it is. Suppose that A and B1 belong to C-star algebra A. If A is positive and A is less or equal than B1 star B1, then A belongs to this here. So what is this? This is C-star algebra. It's called hereditary C-star algebra generated by, actually it is not generated by anything. It's just a hereditary C-star subalgebra of A. So, just look at all elements of the form B1 star X B1. And that just form a norm closure of those elements. This is a C-star subalgebra, and we are proving that A belongs to it. Now we do it in, it's kind of clear that it should belong there, but we need to prove it. So here is how we prove it. Let for n greater or equal than 1, X and be defined as follows. Oh yes, actually one more thing before that. Since I have to write B1 star B1 many times, let's just call it B. Let B1 star B1, and let Xn be 8 times B plus 1 over n inverse B. Now, B plus 1 over n, this is a self-adjoint element. And not just self-adjoint, you see B is positive. When you add 1 over n to it, it's actually bounded below by 1 over n, which means that this here is a positive element bounded below by 1. So its inverse is in norm at most n. Right, so this is well defined. And
sorry, when you say 1 over n, you mean 1 over n times identity?
Yes, right. So every time I do something like that, I mean, so basically we are always assuming that scalars are subset of any unital C-star algebra. So I just identify complex numbers identify lambda with lambda times 1a. Yeah. So you see, basically, the idea is that this should be Xn should be A, but this is an approximation to A. Now there are two things which are not clear. First, why should Xn's converge to A? We'll have to prove that. And second, why should xn's belong here? Well, it turns out actually xn's maybe don't belong there, but that's beside the point. So let's just proceed with the proof, and you'll see what's going on. So first, we claim that xn converge to A in norm. How do we prove that? Well, it is one of standard tricks. So look at what is A minus xn. So we have to do a few simplifications here. So it's this. Now we can factor out this A. So what remains is 1 minus B plus 1 over n inverse B. Okay, so now I can factor out this B plus 1 over n. And what do I have? So I mean B plus 1 over n inverse. So here I have, let's write it, B plus 1 over n minus B. So when I cancel B and B, here I have 1 over n. So when I multiply that and just do some, just see what's going on, what I get is A times the inverse of nb plus 1, the inverse of nb plus 1. Now, what we want to prove is that this converges to 0 in the norm. So let's see. So it's A minus xn. Norm is the norm of this here. Now, how do you estimate the norm of this? Well, I don't know, but I know how to estimate the square of the norm of that. And that's really what matters. So of course, C-star equality. This here is the same as the norm of MB plus 1 inverse A times A. So it's A squared, MB plus 1 inverse. Okay, so now what now? Well, remember the assumption here was that A is less or equal than B1 star B1. And B1 star B1 is B. So A squared is less or equal than B squared. And here is one of the inequalities that are very useful, right? In this situation, this is less or equal. I'll just write it, although now we are in a billion situation, but I'll just write it down like this. So it's MB plus 1 inverse times B squared times MB plus 1 inverse, close the norm symbol. And now, as I said, this is a billion. And now I can actually go back to square. So this is B times MB plus 1 inverse. Now, why does this converge to 0? Well, basically, it's continuous functional calculus again. So let Fn of t be t divided by nt plus 1. Right, so here, note, we know that b is greater or equal than 0 because b was b1 star b1. Right, so otherwise, this mb plus 1 maybe wouldn't make sense. So this is for t greater or equal than 0 and n is greater or equal than 1. Well, what do we have? Fn of t converges to 0. As n goes to infinity. And moreover, convergence is uniform on any bounded interval. So let me see, do you even need Dini's theorem for that? Or this is just, oh yeah, no, this is triviality, right? Because Fn of t, I mean, this is, actually I was saying this in a silly way, right? So Fn of t is less or equal than 1 over n. So of course it converges uniformly. There is no issue here, right? So Fn of B in norm converges to 0, but this here is norm of Fn of B. Okay, so we proved that Xn converges to A in the norm. Okay, but so what? Let's just go back. So we are trying to prove that
Sorry,
A belongs...
can I ask you
yes.
a silly question?
Yes.
In the inequality, you have an inequality. Now it is not shown. Yes, here it is shown. Above, here, this inequality.
Yes.
Why you can pass from A squared to B squared? You just know that A squared is less or equal than B squared, but how?
This is a standard. This is a standard trick. So you know that if A is less or equal than B, greater or equal than 0, then if you take X A X star, it's less or equal than X B X star for every X. This is just standard. I mentioned it, several weeks ago. Mm-hmm. It's straightforward to check. Basically, I mean, I actually don't even have to check anything. This is the same as saying B minus A is greater or equal than 0. And this here is just saying that X times B minus A, X star is greater or equal than 0, which is immediate then. Okay. So is this okay? Okay, I assume that it's either okay or that Mateo's connection.
Yes.
Okay. All right. So where was I? Right. So what I wanted to say is that we now want to check that A belongs to this algebra, but of course, if you could prove that Xn belongs to that algebra, we would be done. But it's not obvious. But now let's see what Xn is. Actually, let me just copy this. I don't have to rewrite it. So it's trying to economize its space. So now Xn is this. Now what? Oops. Sorry, my pencil was in the wrong mode. Here. Okay, so what this means is that Xn star Xn, well, look, what does Xn star Xn look like? Well, it is B blah, 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 B. Never mind what is in the middle, but there is B at the beginning and the end, which means that it belongs to this algebra BAB, and that subalgebra, it is a subalgebra of B1 star AB1. So okay, now because Xn converges to A, Xn star Xn converges to A squared. And therefore, A squared belongs to B1 star AB1. Okay, but now we use the fact that A is positive once again. So since A is greater or equal than 0, A is equal to, well, the square root of A squared. And therefore, A belongs to C star algebra generated by A squared. And that is a subset of B1 star A B1. Right. So this was, you could say this was a lot of work, but the proof uses a trick that is being recycled over and over and over. Let me just roll back to that. You see, it's somewhat naive, really, but it works. So The point is just to write down this expression here. You would want to write something like A is equal to B inverse B, or something like that, and prove that this works. But you know, this trick with looking at B plus, you know, replacing identity with B plus 1 over N inverse times B, and using C star equality to make estimates is really useful. Now, the next lemma is something that I originally planned to prove in detail, but the proof is basically elaboration of what we just did. So I'll just read it carefully and basically tell you how to start the proof and try to convince you that continuation is really just applying C star equality and this trick that Matteo asked about several times, and it works. Now, okay, proposition is very general, but it's also very useful because of that. And proposition is lifted from Gert Peterson's book, C algebras and their automorphisms, which is really great book. I mean, it's not the easiest book to read, but it contains a wealth of really quite sophisticated material about C algebras. Anyway, so here's the statement. Right, I warned you, right? So it's not easy to read. Let's just see what's going on. So you have B, C, and D in some C algebra A, and two continuous functions. Now you see by looking at this here, you can see that those functions will be applied to B. Actually, B is a positive element. So you can see that F and G are chosen in such a way that F of B and G of B makes sense. That's the only thing here. And another thing is that H of T, F of T, G of T, T inverse continuously extends to this interval here. Now, what that really means is that this expression has a finite limit as T approaches to 0. Because any other point is not a problem, right? So you have product of three continuous functions, it's continuous, just T inverse is not defined at 0. So all that we need is that this limit exists. And basically F and G are taking weight off in two opposite directions. Now here are the key assumptions. C star C is less or equal than F of B squared, and D star is less or equal than G of B squared. Then this sequence AN, which is formed as C times B plus 1 over N inverse D, norm converges to a limit A, and that limit has the property that norm of A is less or equal than norm of H of B. Now, how does one prove that? So as I said, I am not going to prove it, but essentially you want to estimate the norm of this, and you can say norm of this squared by using exactly the same trick that we had before, but you know, just flipping this around a few times by using C star inequality and using this basically, you need to use both of these assumptions that C star C is less or equal than F of B squared and D star is less or equal than G of B squared. And just one difference from what we had in the previous case, at the end, you know, we got this function B times NB plus 1 inverse, which was obviously uniformly converging to 0. Here, it's not going to be obvious to actually have to use Dini's theorem, that you have a sequence of continuous functions which are bounded above, pointwise converging to something, convergence is uniform. And that's the proof. So basically, you've seen all the ideas for the proof of this. And this, I'll say a few more words about this. These can be used in many situations. But I'll just proceed to corollaries that we actually need here. All right. So here is the corollary that we need. Okay, and now I have to, I'm not sure if I said something about polar decomposition. So let me just say, I forgot. I don't think I said anything. Okay, so theorem. So if you have an operator for every b of h, there exists v, partial isometry, such that b is equal to v times absolute value of b. Absolute value of b is defined as the square root of b star b. Now, this is not true in C algebras. So if you have, let me just say, note, v does not belong to C star of b for some b. Basically, if you have some compact operator, which is not a finite rank, then typically v is not going to be there. Now, why is this theorem useful? Well, this is exactly what you need to get that property of phi star that we talked about, but we'll leave that for a moment. So here, this corollary talks about polar decomposition of B. And you see, part one is a poor man's version of saying that V belongs to C star of B. So what part one says is that if G is a function which vanishes at zero, a continuous function on the spectrum of B, then, oh, okay. So what I should have said, it's spectrum, okay, I should just say G of 0 is equal to 0. This is what I meant when I wrote this here. Right, so G vanishes at 0, then V times G absolute value of B still belongs to C star algebra generated by B. Right, so V is not there, absolute value of B is there, but you can do something. And okay, two more properties along the same lines. So if A is a C star algebra and B belongs to A, and C is in this algebra that we saw in previous lemma, B star AB closure, then V times C belongs to A. And finally, if A is less or equal than B star B, then VA belongs to C star of AB. Okay, so let's look at the proofs. So proof of one, what is the point here? Let me, yeah, okay, so again, it's the same kind of trick. So let AN be B times absolute value of plus 1 over n inverse G of absolute value of B. Right, so you see, if you replace, if you just let n go to infinity, then B times absolute value of B, let me just write it on the side here. If you look at, I mean, if absolute value of B is invertible, then B times absolute value of B inverse is V. Right, so this is more like, oops, sorry, what did I do? Right here. So this is more like wishful thinking, but it gives you a hint of what is going on here. Okay, so this AN, by the previous lemma, we want to use the previous lemma to check that AN is indeed a Cauchy sequence. And let's see. So and let's see, what do we have? First, B star B is less or equal than, well, it's equal to absolute value of B squared. If you look at, I have to look up this proof. It's somewhat tricky. So right. And okay, G of absolute value of B is already less or equal than, okay, I'll just write it, although it's kind of silly. This is less or equal than G of absolute value of B. So what is the point here? That if I look at G of T times T times T inverse, exactly. So this is continuously extends. So this is continuous on the interval from 0 to norm of B. So by the previous lemma, so by this big lemma, this sequence AN is Cauchy. And what this sequence converges to, well, actually, I don't even need to use the lemma. A minus AN converges to 0 as again goes to infinity. And this can be proved again by using the same tricks. Right, so use the same trick as before. And now what that means, so call them, what were we trying to prove? Oh, when I said A. When I said A, what I meant was V times G absolute value of B. This is what we want, right? Basically, here is G absolute value of B. B here is equal to V absolute value of B. And the whole point is that it absolute value of B times absolute value of B plus 1 over N inverse effectively converges to 1 when squeezed between these two. So trust me, the same proof as before. And therefore, right, so basically what this means is that V times G of B belongs to this C-star algebra to which all the ANs belong to, and that C-star algebra generated by B. Okay, I'll just have to scroll back. Any questions before I scroll back? Okay, so for part 2, if a C-star algebra B is in A and C belongs to this closure, then VC belongs to A. Pretty much the same proof. You just okay. 2 is like 1, but just put C in place of G absolute value of B. Right, exactly, you know, A answer. So this is the only difference, that C is going to be here, and all the estimates are basically same. And part 3 is just really special case of 2. Part 3 was A is less or equal than B star B. And well, if A is less or equal than B star B, then we already proved that it belongs to this. So 3 falls from there. Okay, so if there are no questions about this proof, you see, I get nervous when it comes when there are too many epsilons. So please do stop me and do complain if I say something funny. I actually went to discrete mathematics because I wasn't much into epsilons, but look at me now. Anyway, so now we need to prove what I promised before. So back to phi star. Okay, so fix A, which is in B of H. A is equal to V times absolute value of A. Actually, I don't care about that. Sorry. I don't care about A. So let A0 in B of H be such that P of A0 is phi star of P of A. All right. Now, I hope you're not going to kill me now. We just need the polar decomposition for A0. All that work that I did was for arbitrary multiplier algebra, but I really wanted to go over this continuous functional calculus. So then A0, we can write it as this. It's polar decomposition. Now, in particular, because V is a partial isometry, its norm is 1. And now let F mapping. So basically the same trick as before, F mapping R to R. So F of T is minus norm of A0 if T is less or equal than minus norm of A0. It is equal to T if T is in between. And it's norm of A0 if T is greater or equal to the norm of A0. And just let phi star of A be V times F of the absolute value of A0. Right, so the norm of this is at most the norm of F of A0, which is the norm of, let me write it down. So norm of V times F of absolute value of this is less or equal than norm of V times norm of A0, but norm of V is 1, so it's less or equal than norm of A0. Now, the point is that even if we were not in B of H, we would be able to do this because you see this element here, it even belongs to C star of A0 because F at 0 is 0. Okay, so at this point, we can produce lifting which is good enough for what we're going to do next. And we just have enough time to do something, some basic set theory. So I guess set theorists can probably take a nap now, but something that we are going to need as soon as we start working on liftings. There is a side remark. Basically, all this continuous functional calculus machinery, it can be, it is important component, not everything, but important component in the proof of a great theorem called Kirchberg's slice lemma. I'm not going to state it, I'm not going to need it, but if you're working with tensor products, this is one of the most useful theorems in tensor products of C algebras. So you may want to look up. Everything is in my book. Complete proof is there, yeah, this is a super useful theorem. Okay, so next, just a few standard tricks from set theory, and you'll see very soon why do we need spaces like this when analyzing Calkin algebra. So suppose that we have a sequence of finite sets. Well, at least two elements each to make this non-trivial. Now, if X is set of natural numbers, then dx is just product of those dn's such that the corresponding index is in X. And this space is compact when we take a product topology. And product topology is given by this metric d of AB is 1 over what I call delta before, minimum n such that an and bn disagree, plus 1. And if you look at the entire product dn, the basic open sets, right? We had something very similar recently, but now I'll just have to be slightly more precise. Basic open sets have this form. Notation is slightly different from what we had. I comma r, here I is a finite subset of natural numbers, and r is in this product di. Right, so what does this look like? Well, here we have dn plus 1 to dk. So I'm choosing an element in each one of those, and if this is I, so what does IR look like? Well, anything that does whatever in the remaining part of product, but on the interval I exactly agrees with these chosen coordinates, and then later you can have whatever you want. Before we just took I to be initial segment of natural numbers, finite initial segment, but here it's going to be important to have these more general open sets. Okay, so here is Lemma. Just a few observations about these. If intervals I and j are disjoint, then the intersection of these basic open sets is non-empty and of this form. You have I union j, and Rs, it's really concatenation of R and S. So what do I mean here? Rs of I is R of I is if I is in I, and at some j, it is S of j is if j is in j. Right, so basically proof is, Ri is those elements that pass through certain points when you're in I, and Js is those that pass through certain points in J. Intersection is just requiring both, right? It's important that intersection of I and J is 0, is empty set because you don't have contradictory requirements on these two. Right, and 2 is immediate consequence, right? So it's if intervals are disjoint, then the intersection of these is non-empty. And also when, relation between two of these. So when does IR include JS? Well, if and only if the requirements that IR that it puts on its elements are weaker than those for JS. And that means that first, I is a smaller set, right? So you just have fewer requirements, and also that requirements agree. All right, so I'm going quickly over this, but let me know if something is not clear. So again, to set theories, this probably, this is used all the time, but if you haven't seen it, please let me know. Okay, so right, why did I add a page here? I don't know. So here is a theorem. Now, when I say co-meager, let me just, so meager just means of first category. Right, and co-meager means complement of a meager set. Equivalently, it means includes a dense G delta set. So first one was definition. The second one is really a theorem. So co-meager, if and only if includes dense G delta set. Here I'm talking about subsets of a Polish space. You don't really need the Polish space, you just need the bare space, but let's not bother defining bare spaces. If you have complete separable, completely metrizable separable space, this is the case. So anyway, subset of this product space Dn is relatively co-meager if and only if, and here is a combinatorial characterization of what it means to be co-meager. So there is a sequence of disjoint finite subsets of n. You can choose them to be intervals, so it's not loss of generality. And for each one of them, there is Sn, which is this product indexed by I of n, such that the intersection over all m of the unions of tails n greater equal than m of this is subset of A. Now you can see that indeed, this here is a G delta set. So this is open, right? So union is also open. And when you intersect countally many, this is G delta. Moreover, this is a dense G delta. So let me just prove first the easy direction. So proof, right? So the easy direction is the converse direction. So I need to check that this set is dense G delta. Well, I already checked it's G delta. So I need to check that this intersection over all m union n greater or equal than m I of n S of n is dense. Oh, okay, so just fix some non-empty open set. And I can as well fix a basic open set. So fix some JR. So I need to prove that, what do I need to prove? I need to prove that my intersection hits this set. Now, since I of n are disjoint, and since J is finite, well, at most finitely many of them can intersect J. And so for all but finitely many n, I of n intersect J is empty. Okay, but now what that means, but then right, by that lemma, JR intersected with I of n, S of n is non-empty, but you see that I of n, S of n occurs okay, so sorry, I was too fast here. Okay, fine, okay. So this is non-empty. Okay, so I'm not proving this in the optimal direction. Okay. Okay, sorry if you see what I'm going to say, but I'll have to say it. So the right way to prove it is that, okay. So the right proof is the following, that for every m, this union n greater or equal than m of in Sn is open and dense. Right, it's clearly open, it's union of basic open sets, and it's dense by what I just said a moment ago, right? And so this here is intersection of open dense sets, so by bare category theorem. Right, so basically I just realized that I was about to be forced to reprove the bare category theorem, and there was obviously no reason to do that, right? So use bare category. All right. So we come to the interesting direction, the one that we are going to need later on. So fix a subset of Dn, which is comeager. Yep. Right. So as we said, what that means is that A has a subset which is a dense G delta set. So fix dense open Un subset of Dn for n in n, so that the intersection of UNs is subset of A. Now, one minor matter of convenience, just like in proof of bare category theorem, you can intersect first finitely many dense open sets and replace UN with them. So we may assume without loss of generality that U0 includes U1, includes U2, and so on. And so this is a decreasing sequence of sets. Okay, so now we can proceed to find our parameters. So find I of n, S of n by recursion. Okay, so first, fix I0, S0, so that I0, this interval is subset of interval of the set U0. Well, we can do it because U0 is dense open. All right, so that wasn't interesting. Now, next. Now, let's see what does I0 look like. Actually, this is going to help. So not really help, but just to make a proof slightly less technical, I will assure each in is an interval. Now, enumerate di0 as Vj for j less than k0. You see, this is an important point, that this is a finite set, because it is a product of finite sets, product of finitely many finite sets. So we just enumerate its elements. And now find ij1 and sj1 for j less than k0 as follows. So first, remember, U1 is a dense open set. So what we want is that I0, S0 intersected with I0. Oh, sorry, no, I don't want S0 there. Definitely don't want that. I want V0 intersected with I01, S01 to be subset of U1. Right? How can I assure this? Well, this is a non-empty open set. Right, so it's a non-empty open set, and now U1 is an open set, which is dense. So there is a non-empty intersection. Now that non-empty intersection contains a basic open set. So I just find this basic open set there. Okay, now next, what do I want next? Well, I took care of V0. So now I look at I0, V1 intersected, let me call this W0. No, that's not W0. Intersected with this guy here again, I01, S01. Now this is again a basic open, this is again non-empty open set. So I have the same picture here, non-empty open set, and U1, there is something in the intersection. So here, and that again, I can assure that it's a basic open set. It will be I1 of 1, S1 of 1. Why are they of this form? Well, you see, if I have a subset of a basic open set like this, what do basic open sets look like? Well, I'm just fixing more and more coordinates. And so the set I1 is this set on which I'm fixing more coordinates, and S1 is those coordinates that I'm fixing. And so, etc. So what we assure is that I0 Vj intersection, now here I have L goes from 0 to J, I think, yeah, of I L 1, comma SL1. Oh, I forgot to say, this was subset of U1. Right, so this is subset of U1. Right, so this is basically the same idea as the idea in the proof of bare category theorem. You have a dense open set, and you're just choosing decreasing sequence of basic open sets, except that here sets have some structure. These basic open sets are all of this form, just freezing finitely many coordinates. And the key trick in the proof is, you see it here, we are just changing this set of coordinates we are fixing. You know, we are taking care of I0, and we can list all possible candidates for what restriction of any element on I0 can look like. There are only finitely many possibilities. You just exhaust the possibilities, and here you just keep on adding these intervals. Right, so note that I L1 intersected with I L prime 1 is empty if L is different from L prime, right? We are just freezing more and more coordinates. And now once we are done, what is I1? I1 will be just the union for L goes from 0 to, I think it was K0. K0, yes. K0 minus 1 of IL of 1. And what is S of 1? Well, it is just a concatenation. So it's S 0, 1, S 1, 1, da, 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 S K0 minus, K0 minus 1, 1. Right, and this is our first candidate. And now for the next one, we just do the same, except now I'll just draw the picture. At this point, we have I0 and we have I1. Now I1 is quite long, right? So it's union of this large family of finite sets. And now you just list again all possible finite, all possible elements of D sub I0 union I1. This is a finite set again. And then just keep on meeting different elements that start like this and entering set U2. So here you just choose sequence of finite disjoint intervals. There are as many intervals as the cardinality of this set here, so that no matter how you choose the initial segment, what comes later is going to assure that you meet U2, and so on. Right. So let me just say it instead of writing it down. So the idea is that we choose this infinite sequence of finite sets in such a way that no matter where you take first finitely many elements to your set, then for no matter how your what happens on first finitely many elements, if on the next element you actually agree with it, and by agree I mean that you actually belong, so that any x that belongs to this implies that x belongs to the n set. But for any n, for every x. So this is really the key. It just doesn't matter what happens before that point. Now, what that means is that if there are infinitely many n's such that x belongs to this interval, then there are infinitely many n's such that x belongs to un. But you see, because at the beginning of the proof, we made sure that un's form a decreasing family, this it means that x belongs to the intersection of all the un's, which means that x belongs to A. Right, so this is a standard trick that is one of the reasons why product spaces are so well behaved. Okay, I wanted to state one more theorem, but I have 2 minutes until the end, so I don't think I should rush it. I'll just do it at the beginning, and then you'll have more product spaces in what comes after. Any questions? Okay, so so thank you, and I'll see you on Monday.
Sorry, could you go back to page 6?
Of course. To where? Oh.
Page 6.
Page 6. You'll have to tell me what was on page 6. Which one? Okay, I'll just you just tell me stop. Wait, I don't even see page numbers here. But anyway, you just tell me where to stop and. Still?
Yeah, keep going. You can see the page numbers in the bottom right.
Oh, yeah, right. Yeah, I was, okay, here. This?
The last line on this page.
Oh,
Why
yeah.
is the first equality true?
Okay, so that's the spectral mapping theorem. But let me see, how can I convince you that spectral mapping theorem is true? Like this. So B is self-adjoint. Should be continuous functional calculus. You see, P is a star homomorphism. Let me just put one more page. Is this? Yeah. You see, P is a star homomorphism, and what? Okay, so basically that's the proof. Let me. Sorry. How do I say it? It is, oh yes, thank you. Thanks to Finlay. It's true for polynomials and stone wires, as it implies it's true for continuous functions on a spectrum. Exactly, right. Right, so like, so if I had P of B to N, it is P of B to N and so on. Thanks, Finlay. All right, yeah, thank you. So yes, but anyway, yeah, thanks.
Thanks.
Well, thanks to Finlay, not to me. Any other questions? Okay, if not, then I'll see you on Monday. And take care, and bye.